All right, let's start. Today we will prove Burnside's theorem. So let's first look at its statement. So it says that if P and Q are primes, then the theorem says, which is known as Burnside's P to the power A and Q to the power B theorem. This says that every group of order P to the power A, Q to the power B, where a and b are non-negative integers and a plus b is at least 2, then g cannot be simple. So this again, let me repeat, any group of order p to the power a, q to the power b, when a and b are non-negative integers with sum at least 2, cannot be simple. So this theorem, which is known as the Burnside's p to the power a, q to the power b theorem, as I just said, uh, that has the following consequence. So the above theorem that implies that every group of order p to the power a and q times q to the power b is solvable. Just to see how this follows from the Burnside's p to the power k, a q to the power b theorem, we will apply induction on a plus b. So from the Burnside's p to the power a and q to the power b theorem, what it says that if g is if a plus b is greater or equal to 2, then applying that we get that g is not simple. So therefore g has a normal subgroup which is non-trivial and proper. So let such a subgroup be H, then both H and G mod H, since the orders of both of them is a divisor of p to the power a, q to the power b. So both H and G mod H have order of the type p to the power something and q to the power something, and then but the powers will but the sum of the exponents of p and q will be certainly less than a plus b, because H is proper and non-trivial. So therefore you are allowed to use induction, and you obtain that both H and G mod H are solvable. Now, when we discuss solvable groups, we prove the following theorem that if G is solvable, if and only for every normal subgroup N, both N and G mod N are solvable. Okay, so this is the argument for A plus B when A plus B is at least 2. The other case, that is when a plus b is 0 or 1. So in 0 case, we should not bother about that at all. So in a plus b is 1, so that means either a is 1, b is 0, or b is 1, or a is, b is 1, a is 0. So in that case, it's see that then it's in that case the order of G becomes some prime, and certainly so it's a group of prime order, so hence it is nilpotent and consequently solvable. So thus we have proved that every group of order p to the power a and p to the power b is solvable from the Burnside's p to the power a, q to the power b theorem. Okay, so let me just again go through the argument once again. So this is our theorem, Burnside's theorem. So this as a consequence of this theorem, we get p to the power a, q to the power b. Every group of order of this type is solvable. So how to do that? We will do induction on the sum of the exponents. In the case a plus b is greater or equal to 2. We get from the theorem we get there is a intermediate normal subgroup. So we take that subgroup and take the quotient with respect to that. Both of them will have order of this type, but the sum of the exponents there will be less, because both of them are proper divisors of this p to the power a, q to the power b, which is the order of G. Now we use induction. In the case when a plus b is 1, then it's already there, it's obvious. All right. So now we will focus on the proof of this theorem of Burnside. Okay. basically what we will do is we will prove this theorem from another theorem of Burnside, which is also quite interesting in its own right. Okay, so let me just again tell you that this is what we have derived from the Burnside's p to the power q to the power b theorem. Usually in textbooks, Burnside's theorem, by Burnside's theorem, most of the textbooks mention this one. Yes, it's also proved by Burnside, but actually he proved something. Even more, from which this follows as a corollary or as a consequence. Now, this theorem of Burnside that also will be derived from another theorem of Burnside, which is also interesting in its own right. Okay, so we proved this from this. Now we will prove from this theorem of Burnside. All right. So first, let's see that how to derive Burnside's p to the power a b to the q to the power b theorem from this. Let me repeat. So we now assume this, and from that we will see how we can prove the Burnside's p to the power a times q to the power b theorem. Okay. So, well, so before that, let me say one thing, that in the condition, the statement of Burnside's p to the power a q to the power b theorem, this condition p to the a plus b at least 2 is you can say the condition is appearing. So in fact, this condition has to be there, because otherwise, if a or b is a is 1, b is 0, then you see the group has order, some group has some prime order, so it has to be simple. So this cannot be true if one of them is 0. This cannot be true if a plus b is less or equal to 1. Okay, a plus b is less or equal to 1. So this condition is important. Now let's come here. So as I said, here our assumption would be a plus b is at least 2. So first we look at the case when a is 0 or b is 0. Okay. So let's try to see. So okay. So first of all, I forgot to mention that we will prove Burnside's theorem from this, and our method of proving will be by contradiction. Okay. So we prove by contradiction. So now we will assume that G is simple. Okay. So let's simple. So let's first see that the conclusion is clear when a is equal to 0 or b is equal to 0, because then the order of the group will be the power of some prime, and for such groups we have proved that the center is non-trivial. Now the center is a non-trivial, and also center is a normal subgroup, so therefore center has to be whole of G, right? So center has to be whole of G means G is abelian, and you see G is abelian, finite abelian, G is simple. In that case, you see G has to be of some prime order, because we know that we have seen in fact that for any finite abelian group corresponding to any divisor of the order of the group, there is a subgroup, and since it's abelian, so subgroup is to be normal. So a finite abelian group cannot be simple unless it has prime order. But you see here, since a plus b is at least 2, so it cannot be just the order cannot be just a prime the order cannot be just what I mean is the order of the group cannot be just p or q. Okay, so the conclusion is clear if a equal to 0 or b equal to 0. So therefore now we assume both of them are positive. Okay, now we will use Sylow's theorem. So what does Sylow's theorem say? It says that there is a subgroup of G, let's denote that by Q, of our order Q to the power B. Okay, so thus Q is a subgroup of order or subgroup with order some power of prime. So again, Q has non-trivial center. Okay, so if you pick any element from the center of Q, what I mean is if you just take any non-trivial element from the center of Q, because there's taking identity doesn't make any sense and it doesn't give us anything. So maybe I should have mentioned that G is a non-identity element. I should have mentioned, but somehow I forgot. So you consider G is a non-identity element from the center. Now what is clear that since it is from the center, so any element of Q will commute to that. So that means any element of Q is in the centralizer of G. So therefore, Q is contained in the centralizer of G in the group G. Okay. So any element is the center. Okay. Okay, just a minute. I think here you don't need to insist that G is not identity. In fact, if G is identity, then that case will be discussed later on. Let's see. Then that case will be covered later on. So let's see. So Q is contained in the Q is contained in the centralizer of G in the group G. And now what does that say? So if this is so, then the centralizer has order more than Q to the power B, and a centralizer has order at least Q to the power B. So therefore the order of the conjugacy class, which is by orbit stabilizer theorem order of G by the stabilizer, that is here the centralizer, must be some power of P. Okay, must be some power of P. Okay. So the where R is a non-negative integer. Okay. So now you have to see that R cannot be greater or equal to 1 because the theorem that we have assumed to derive the Burnside's theorem is the following, that if a finite group has a conjugacy class of some prime with order some power of a prime, then that cannot be a simple group. So, but here we have, while proving the theorem by contradiction, we prove J is simple. So that shows that here R cannot be greater or equal to 1. Okay, then it will be, then it cannot be simple, it's a contradiction. So there R has to be 0. Again, R has to be 0. What does that mean? R 0, that means that G is the centralizer. So, so R that I mean, so yeah, so R is so R is 0 means G is the centralizer of G in G. So therefore, every element of G, every element of the group G commutes with G. Okay, yeah, I was right that here you have to take G as a non-identity element because this is where we are going to need that. So since G is a non-identity element which belongs to G, then that forces ZG to be non-trivial. The simplicity, from simplicity, we get ZG has to be whole of G, that is G is abelian, which is not possible as we have argued before. So yeah, as I said that here you have to take G's which is non-trivial, which is not identity, and that you can do in view of this. So for you, let me just again quickly go through the argument. So what we are doing is the following, that we prove by contradiction. We prove the Burnside's theorem from this, from another theorem of Burnside's, which says that if a finite group has a conjugacy class of order some p to the power r, where p is a prime and r is a positive integer, then G cannot be simple. So the proof is by contradiction. The proof is clear when A or B is 0. So we assume A and B both are non-zero. Now you apply Sylow's theorem. That gives you a subproof which is order q to the power B. Where again, since B is positive, so that has center non-trivial. So we pick non-identity element from the center. Remember, non-identity will be required later, so which we must mention that, which I forgot to mention, but you should mention that. Okay, so it is clear that this is happening. So since this is in the center of Q, so every element of Q commutes with G. So thus the centralizer contains Q. That shows that the order of the conjugacy class is some p to the power R. R cannot be at least 1, because then from another theorem of Burnside's theorem we get G, we get G must be simple, which is, we get G cannot be simple, which is a contradiction, which is a challenge to our assumption. So if R is 0, R is 0 means centralizer of G is the whole group G. That means every element of capital G commutes with small g. So that means small g is in the center. Once small g is in the center, because we have taken small g such that it is non-identity, so center becomes non-trivial. From the simplicity assumption, center has to be the whole of group. That means again G is abelian. As I said earlier, that an abelian finite group must be of order some prime. But here, since it has order p to the power q to the power b, where both are positive, so that cannot happen. So in view, so the Burnside p to the power q to the power b theorem is proved modulo this theorem of Burnside. So we now focus on the proof of this theorem. Okay, so in the next video, I will prove this theorem. So yeah, in the next video, I will prove this theorem with the help of a lemma. So the first we discuss a lemma. So from that lemma, we prove something which implies this theorem. Okay, so we stop now, and yeah, I hope that the chronology is clear, that this is the main theorem which proves, which shows, which actually gives us a large class of solvable groups. And this theorem is derived from another theorem, interesting theorem of Burnside. You should note that all this theorem of Burnside, all these theorems of Burnside are actually saying a lot about the structure of finite groups. And then we saw that how this theorem yields the Burnside p to the power q to the power b theorem. And so that we are now left with the proof of this. As I said, we will prove this in the next video. Okay, okay, I stop here.